throughout this course, we're going to be dealing a lot with systems of equations. So what I mean by that is something where you would have seen it in algebra before with 2 equations and 2 variables, maybe even 3 equations and 3 variables. With 1D motion, we're going to see that that happens when we have, say, 2 objects that we're analyzing in the same system. And so then we can write an equation for each object, and then we have a 2 equation, 2 variable system. The earlier that you start thinking about the physics problems as equations of systems of equations, then the better off you'll be for the rest of the course when things get more complicated. So again, for these 2 equation, 2 variable systems, what we want to do is to have the simple goal that we want to have 2 different equations that have the same 2 unknowns. So we have this 2 equation, 2 variable system. So we want to end up with 2 equations that have the same 2 unknowns. And the unknowns are sometimes also called the variables of the system. So 2 equations, 2 variables, sometimes 2 equations, 2 unknowns, whichever one you're more comfortable with. But the idea is that it is a system of equations. So as a very simple example with 1D motion, let's go ahead and look at this problem. So in this problem, we have 2 objects that are both moving with constant velocity motion. We have a runner, and then we have a bird. And it's a hypothetical situation, and it involves a little bit of magic. I always call the bird the magic bird, and you'll see why. So here we have the marathon runner, and they run at a steady 15 kilometers per hour, meaning that their velocity is constant. If the velocity is constant, then we know that the velocity is simply just going to be equal to the distance over time. The instantaneous velocity equals the average velocity. And so this is true for constant velocity motion. Okay, so when the runner is 7.5 kilometers from the finish line, then there's a magic bird, and the magic bird is going to fly at a constant speed of 30 kilometers per hour. And so when the bird reaches the finish line, it instantaneously changes direction and flies back to the runner. That's the magic part, and that there's no slowdown, no speed up time. It's just like boom, boom, always 30 kilometers per hour, constant velocity, magic bird. So this is what happens, right? The runner is running at a constant rate, and then the bird just boop, 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 back and forth. And you're asked to find how many kilometers does the bird travel. Now, you could solve this, and you might even be able to solve it kind of just thinking about the situation. But what I'm asking this one for is very specifically so that we can write out what 2 equations and 2 variables that are used to solve this. So not so much getting the answer, because we don't really care. It's a hypothetical made up situation, but what we do care about is the process. How do we write this as a system of equations? Once you can take a physics problem and reduce it to a system of equations, you then just have an algebra problem, and you just have the math. You get the physics done, and then you do the math. So for this specific situation, the way that it works for our 2 equations and 2 unknowns is that we want to have an equation for each runner. So you want to have, for each object. So have an equation for each object. And so you'll have an equation for the bird, and you'll have an equation for the runner. So in this case, the general equation for constant velocity motion, as we just saw, is that delta x is equal to Vx times t. You want to think about what your 2 objects have in common. Very often, they're going to have time in common. And so what we can do then is say that time is going to be one of our variables. So t is a common variable. So it should be in both of our equations, because the bird and the runner, that's basically what it's asking, is how far does the bird go before the runner crosses the finish line? So they have the same time. The other thing in terms of identifying your second variable is to often ask yourself, what do you want? What's the problem asking for? And in this problem, it's asking for how far did the bird go? So delta xb, say for bird, is what we want. And that's going to be equal to the other variable in our system. So generally speaking, for our two equations, two variables, one of them will be something they have in common, say time, or if they hit each other, right, like then their location at some time. And then also what you want, or else you're just writing a random system of equations, but you're not actually solving the problem. So we have our two variables, and now we just need our two equations. And I chose this easy example because this example uses constant velocity, which means you don't have to hunt through the kinematics equations to find which equation to use for each object. Instead, you want to just use this constant velocity equation for each object. And it'll look, you can use the same object, but with separate subscripts. So our system will then look like this. I will have that the delta x of the runner, so delta x of the runner, that's an R, is going to then be equal to the velocity of the runner times the time. That's going to be one of my equations. I can label that equation 1. And then equation 2 will be delta x of the bird is equal to the velocity of the bird times the time. And this is my final system of equations that I could solve. Because if I look at this, in terms of my two unknowns, t and xb, that's how they show up in my equations. And I know everything else that is in here. So I already know that I know how far the runner goes, I know the speed of the runner, and I know the speed of the bird. So those are known quantities. So I now have a system of equations that I can solve this problem with. So in one of your problems today that you'll work through for module 2 with two objects, it will be one where somebody throws a ball upward from the bottom and somebody else is dropping a ball from a window above. And the question is like, when do they hit? So you're going to have one equation for this person's ball, and you'll have another equation for the other person's ball. And then you want to decide, you know, where they collide, what the final position is at the same time. So you'll go through the same process. You'll have one equation for one ball, another equation for the other ball, and you'll have a system of two equations. So one thing to keep in mind is that you always are going to use the same coordinate system for both equations. For the bird and the runner, it was pretty obvious because they both ended up at the same finish line. But for example, when you have this one that you'll do in the problem where you have like somebody's dropping a ball out of a window and then somebody else is throwing one up from the bottom, you want to just take y equals 0 down here for both. Use that for both objects so that when you talk about a position, it's the same position, it's the same coordinate system for both objects. All right, so that concludes this video on how to handle two object problems and also how that fits into the bigger goals of this course of just really understanding and be able to write things as a system of equations. Let me know if you have any questions.